This is lesson 12 of the Quantum Mechanics, a mini lecture series titled Light Spectra. So as I discussed before, in the latter half of the 19th century, particularly in Europe, scientists were studying the light emitted by different elements, typically in their gaseous form, but they couldn't make sense of it. And there was already the black body radiation problem that existed, and there was the photoelectric effect as well, which classical physics failed to explain. So these two phenomena here, classical physics couldn't explain. There was a Scottish physicist named Thomas Melville, and this guy was the first to really notice what was happening. Okay, so what he did was he had some hot gas, passed it through a slit. Okay, so he sampled only a bit of light. That's what a slit does. So a hot gas, elemental gas, passed it through a prism. And the glass prism, if you remember, splits, it disperses, in other words, splits the light into its colors. And here's an observation screen, and you get only very specific colors, okay, with the black background. That's called an emission spectrum. Emission spectrum because the hot gas is emitting very specific colors of light. For example, sodium, right? And the conclusion was that different gases, different elements, have different patterns, different spectra. And so this technique, also known as spectroscopy, became a very powerful technique to identify unknown elements, particularly in astronomy. Okay, that's how astronomers determine what elements make up a star, by just studying the spectra. And this was actually how helium was discovered in the sun. Okay, the scientists were looking at the sun's spectrum, the solar spectrum, and they found corresponding lines which matched that of helium on the ground here on Earth in their labs. And so that's how helium was discovered in the sun. And helium comes from the word helios, Greek for sun. And physicists at the time thought that the key to explaining these observations came from the stuff making up the gases, okay, the matter, okay. Could it be, particles? Remember, nothing was known about atoms at the time. And so physicists set out to study the simplest of all elements, hydrogen. Okay, it's only got one proton and one electron. It's a very simple element. It's got one proton like this, the nucleus, and an electron going around it. But this picture is, I'm just showing you now for visualization purposes. This wasn't known at the time. I'm just showing you what hydrogen looks like now. We now know that it looks like this. And so a Swiss school maths teacher named Johann, I think that's how you pronounce it, Johann Balmer, he discovered a formula which almost precisely predicted the frequencies of the 4 visible hydrogen lines. So hydrogen emits 4 visible lines in its emission spectrum. Came up with this formula. I'm not going to derive it. F equals R, 1 over n sub F squared minus 1 over n sub I squared. F is the frequency of light emitted. R is just a number. It's a constant, now known as the Rydberg constant. Another physicist down the track refined Balmer's formula, and so the constant is now named after him. And n sub f and n sub I, these are just numbers. These are whole numbers, okay, designed to make the maths work. So Balmer was really trying to figure out a way to make sense of all the numbers coming out of the laboratories, all the frequencies, to see if he can relate them to some relationship, okay. And this worked for the 4 visible lines in hydrogen here, only if n sub f, okay, was set to 0 and n sub I was set to 3, 4, 5, and 6, okay. This stands for final energy state. N sub I is the initial energy state. Okay, so he came up with this formula, but he didn't know what the underlying fundamental physical explanation was of this equation, of this formula, why it worked, okay? That was still the mystery. And just arguments to outline, Rydberg constant is about 3.29163 times 10 to the 15 cycles per second. Okay, that's the unit for it. A very large number. So to summarize, Balmer came up with a formula to successfully explain the observed frequencies of emission spectra.